let's do some calculator work. Make sure that you know how to use your calculator. And the first question is, what do you get for the natural log of 5 thirds? And we're rounding to 3 decimal places. So I'm getting 0.511. If you have any questions about how to use your calculator, make sure you go to the Math Center or ask me, because I want to make sure you are really confident with your calculator. So then B, I'll have 0.536. I'm getting 4.055. And for D, I'm getting about 0.432. So make sure you can reproduce those with your calculator. Okay, so here's some pictures. You know that exponential and logarithmic functions are inverses of each other. So we know that their graphs are reflections about the line y equals x. So here's the line y equals x. This is the exponential graph and the corresponding logarithmic graph. So we also looked at exponential functions where the base was between 0 and 1, and we noticed that they were decreasing. So if you have a base that's between 0 and 1 and you have a decreasing exponential function, then your logarithmic function still is a reflection across the line y equals x, so it's going to look quite different. And then this is the graph we looked at previously with a base that was bigger than 1. So let's also make sure we're familiar with the natural logarithm function. And if your base is e, then e is between 2 and 3. So use your calculator and find e to the 1. It's about 2.718. So it's between 2 and 3, and it's just a number. It's an irrational number that has lots of uses. So there's one other special base. If the base is 10, the result is called the common logarithm, because before there were calculators, this was the most common logarithm, and if no base is written, then it's understood to be 10, because it was used so much that they just got tired of writing 10 all the time for the base. So if you see no base, then it means the base is understood to be 10. So let's look at some transformations. And all the transformations we've already learned all apply here. It's just we're doing logarithmic functions now. So the parent graph is ln of x, or log base a of x, in different places. So the first one, I see a minus 3 in with the x before I do the logarithm. So that's going to shift me right 3 units. That's the only transformation I see there. In the next one, I'm seeing the negative x before I'm doing the logarithm. That's going to reflect about the y-axis. And then the multiplying by a negative after the logarithm happens, that causes to reflect about the x-axis. Okay, then C, I'm seeing an x plus 1 before I do the logarithm. So that's going to shift left 1 unit when the function of logarithm happens. Then I'm seeing multiplying by a 2 after the function. So this is going to cause a vertical stretch by a factor of 2. And then we have the multiplying by a negative after the function, so that's going to cause it easier to analyze. So I'm going to have negative log base 3 of x plus 1. And we're going to put the plus 2 at the end so it's really clear that it's being added, even though you don't see a plus because it happens to be at the front. So we've already analyzed in x plus 1, and so that causes a shift left 1 unit. Then the function happens. Then we see a negative out front. So we're going to deflect about the x-axis. And then the last thing we're seeing is shift up 2. So make sure you're really clear on these. And if you have any questions at all, it can be really helpful to sit with a tutor for just 10 or 15 minutes and have them make up examples and practice working on them until you get it down solid. So the fifth thing in this lesson is solving logarithmic equations. And there's 3 types of equations where you must check your answers. And solving logarithmic equations is one of the 3 because you can come up with extraneous solutions. So remember radical equations, we found that we could get extraneous solutions that didn't work. Rational equations, we could get values that made the denominator 0, so we had to discount that. And then logarithmic equations, we can get values that are not in the domain of the logarithmic function. So we're going to learn 2 strategies. The first is just to solve a logarithmic equation, that there's a log in the equation, and then we're going to use logarithms to solve exponential equations. So first we're going to look at pretty simple equations where rewriting in exponential form is going to be the key. So this first one, 5 to the power of 3 equals x, if I write this in exponential form, so x must be 125. Okay, then b says, here's my base of 3 to the power of 2 equals 3x minus 2. Oh, now the logarithm's gone because I wrote it in exponential form. Then I just need to solve this little algebra equation that I know how to solve. So I'm going to get 11 equals 3x. So x equals 11 thirds. Okay, then c, you have to remember that the natural log has a base of e. So e to the 8 equals e to the negative 2x. So that means 8 equals negative 2x. So x must equal negative 4. And then the last one here, we have base 7 to the power of 2 equals x squared plus 4. And we need to solve for x. So this is quadratic since the x is squared. So let me isolate the quadratic and use the square root property. And the x is plus or minus the square root of 45, also known as plus or minus 385 when we simplify the radical. And then we need to check and make sure this is okay in the original equation. So I have x squared plus 4 as the argument of the logarithm. So think about x squared plus 4. And when is it less than or greater than 0? Always, right? I take any number I want and square it. It's positive at the smallest is 0. And then at 4, it's always going to be positive. So any value of x I come up with is fine. And then the second idea is using a logarithm to solve the equation. So if I have e to the 3x equals 10, I can take the natural log to the power of and ln have the effect of undoing each other. So some students see it as canceling. You can say that to yourself, but really it's the inverse functions of each other. So 3x is the natural log of 10. So to solve for the x, I'm going to divide by 3. And x equals the ln of 10 over 3. So this is called an exact answer. If you are asked to, you can also give a decimal approximation. So there's no exact decimal representation. We have about from 7, 6, 8 down to 15 decimal places. And this is the decimal approximation. So let's look at B. And I'm going to have ln of e to the negative 2x plus 1 equals the ln of 13. The ln of e to a power, both undo each other and leave you with the exponent. And that's equal to the ln of 13. And now we need to solve for the x. So we're going to subtract 1. Negative 2x is the ln of 13 minus 1. And divide both sides by negative 2. And so x equals the ln of 13 minus 1 over negative 2. And this is your exact answer. And if you want to make it really, really clear, you could put parentheses around the ln of 13, because that's the number. It's not the ln of 12, it's the ln of 13, that number, and then subtract 1. So if we want to put a decimal approximation,